Assalamualaikum and hi everyone. My name is Muhammad Fikri bin Muhammad. My matrix number 208257. So today I would like to talk about fluid properties in section A, and after this in section B I would like to talk about dimensional analysis and modeling. So now we continue into section A. So first thing first, introduction to fluid properties. So fluid mechanics is the study of fluids either in motion or at rest. And for your information, both liquids and gases are classified as fluids. So there are some definitions that I want to explain today in fluid properties, which is first density, second specific gravity, third specific weight, fourth viscosity. So now we move on to density. So density is a measure of mass per volume. The average density of an object equals its total mass divided by its total volume. So we can see the formula to find density, which is mass over volume. So it is a simple definition. So next, specific gravity. The specific gravity is the ratio between the density of an object and a reference substance. The specific gravity can tell us, based on its value, if the object will sink or float in our reference substance. It is also can be calculated by the ratio between specific weight of an object and specific weight of a reference substance. So basically, our reference substance is water at temperature 4 degrees Celsius. So there is a picture which is show us how to calculate specific gravity, which is first density of an object over density of water at 4 degrees Celsius, or we can find the specific gravity through specific weight of an object over specific weight of water at 4 degrees Celsius. So the value of specific weight of water at 4 degrees Celsius is 9.81 kilonewton over meter cube. And density of water at 4 degrees Celsius is 1000 kg over meter cube. So next, specific weight. So the specific weight, which is also known as the unit weight, is the weight per unit volume of a material. So it is simple, which is to calculate specific weight, a weight of a material divided by the volume of a material. So next, viscosity. So dynamic viscosity, which is also known as absolute viscosity, is the measurement of the fluid's internal resistance to flow. So the uses of viscosity is we want to know how much the internal resistance of a fluid to be flow. Okay, so to calculate viscosity is the shearing stress divided by the shearing rate change. Okay, so shear stress is defined as a force per unit area acting parallel to a minuscule surface element, which is a tiny surface element. This force is caused by the friction between the fluid particles that will lead to a moving fluid due to fluid viscosity. So I give you an example, one simple example. So imagine there is a container of a fluid. Okay, there is a fluid in the container. So if we apply force to the fluid, it will be moving. Why? A fluid that is in a fluid that is in rest state cannot resist shear stress. So that's why a rest fluid will be moving if we apply force to the fluid. So next, shear rate is the rate of change of velocity at which one layer of fluid passes over an adjacent layer. There is two types of viscosity, which is first dynamic viscosity, which is I have discussed just now. So the second one is kinematic viscosity. So kinematic viscosity is the ratio of the fluid mass density to the dynamic fluid viscosity of or absolute fluid viscosity. So basically it is a mass of a fluid divided by the dynamic viscosity divided to the fluid mass density. So now let's move on to Newtonian and non-Newtonian fluids. So what is the difference between these two types of fluids? So we start with Newtonian fluids. So Newtonian fluid is the fluid that have a constant viscosity with zero shear rate and zero shear stress. The shear rate is directly proportional to shear stress. So basically, Newtonian fluids have constant viscosity. So that is the main point that we must know uh, based on this definition. So next, non-Newtonian fluids. So non-Newtonian fluid do not have a constant velocity and is dependent on shear rate. So Newtonian fluids does not dependent on shear rate, but non-Newtonian fluid dependent on shear rate. So that's the difference. And the example of the Newtonian fluids is water, air, alcohol, glycerol, and tin motor oil. And the non-Newtonian fluid, there have some types of this fluid. So the four types of non-Newtonian fluid is thixotropic, rheopectic, shear thinning, and dilatant. Just now I've mentioned to you the four types of non-Newtonian fluids. So now I would like to explain further about this type of fluids. So first, thixotropic. So the description of this type of fluid is viscosity decrease with stress over time, which means that the longer you apply the stress, the viscosity will decreases. So for example, honey. So when you keep stirring the honey, it will be liquid form. Okay, so that's why we tell that thixotropic fluids, the viscosity will be decreased with stress over time. So next, rheopectic. So the viscosity will increase with stress over time, which means that the longer you apply the stress, the viscosity will increases. So for example, cream. The longer you whip the cream, the thicker it gets. Okay, so that's why we tell that cream is a rheopectic fluid. So next, shear thinning. So viscosity decreases with increased stress. So it means that when you apply more stress on the fluid, it will be more viscous. So for example, it will be less viscous. Okay, so for example, tomato sauce. So when you at home, you want to put on sauce on your plate. So when you open up the cover, so the sauce will not come out as soon as you open the cover. So when you shake the bottle, so it will be easier to for the sauce to come out. Why? Because it is a shear thinning fluid, because the viscosity decrease when you increase the stress. Okay, you shake more, so the sauce will be easier to come out. So lastly, dilatant, the viscosity increases with increased stress. So when you apply more stress, the viscosity will increase. For example, Oblak. So there is a picture of Oblak, which is it is a experimental material. So the more stress you apply, it will be more viscous. Okay, so you can see it have two types of form, which is solid form or liquid form. So when you apply more stress, it will be solid. If you apply less stress, so it will be less viscous. Okay, so that's all the explanation for the types of non-Newtonian fluids. So now let's move on to surface stretch and elastic modulus. So before that, there is some definition that I want to explain to you. So first, stress. Stress is the force applied to a material divided by the material's cross-sectional area. So which means that when you want to calculate the stress, you must have the value of the force and the area. So when you get the both value, so the value of the force divided by area, you can get the stress. So that's how we want to calculate stress. So next, strain. Strain is the deformation or displacement of material that result from an applied stress. So when you apply stress to a material, so there will be some kind of deformation, which is the strain. So how we want to calculate the strain is the length after load is applied minus the original length of the material divided by the original length. So that's how we want to calculate the strain. So after this, I will show you how to calculate elastic modulus. So just now we have learned about stress and strain. So let's move on to elastic modulus. So basically, elastic modulus measure the resistance of the material to elastic deformation. So why we want to find the value of elastic modulus? Because we want to measure the resistance of the material to elastic deformation. So I give you the explanation. So when under stress, materials will first exhibit elastic properties. Okay, the stress will cause them to deform, but the material will return to its previous state after the stress is removed. So I give you one easy example, which is rubber. So when you pull the rubber, okay, it will deform. But when we release the rubber, it will return to its original shape. So that's we call elastic deformation, which is it will deform when we apply stress, but when there is no applied stress, they will go into original shape. So how we want to calculate elastic modulus? It is by the stress divided by the stress over strain. So when we want to calculate elastic modulus, the stress must divided by the value of the strain. So that's why I've told you how to find stress and strain. So next, there is three types of elastic modulus, which is Young modulus, bulk modulus, and shear modulus. So in fluid mechanics, we will talk about bulk modulus. So bulk modulus is the measure of the decrease in volume with an increase in pressure. So the modulus of elasticity of a liquid varies depending on the specific gravity and temperature of the liquid. So I give you example. So when we have a container, okay, we have container and we have fluid in the container. But when we decrease the volume, okay, when we decrease the volume of the container, so the pressure inside the container, the pressure of the liquid will increase, okay, because we decrease the volume of container, but the volume of the fluid stay the same. So that's why when we decrease the volume of the container, inside the container, the fluid, the pressure will be increased. So that's why that's what we call bulk modulus. So there is a table where we can search the value of bulk modulus of some types of liquid. So that's all for elastic modulus. Okay, next we're gonna learn about surface tension. So the property of the surface of a liquid that allows it to resist an external force due to the cohesive nature of its molecules. The cohesive force between liquid molecules are responsible for the phenomenon known as surface tension. So basically, this is the definition of surface tension. Okay, so the property, okay, the property of the surface of the liquid that allow them to resist an external force. Okay, due to the cohesive nature of its molecules. So this is what we call surface tension. So next, surface tension act like a film at the interface between the liquid water surface and the air above it. So the water molecules beneath the surface are attracted to each other and to the surface. So that's why we can see at the image the paperclip floating on the water, because there is surface tension at the surface of the liquid. So that's why that's why I told that the surface tension act like a film between the interface between the liquid water surface and the air above it. So in this example, the surface tension act like a film between the water and the paper clips. So that's what we call surface tension. Okay, so the molecule beneath the surface of the water attracted to each other because of the cohesive nature. So it will attract each other and to the surface. So this is what we call surface tension. Okay, so this allow the paperclip to float. So now we move on to the last topic in section A, which is fluid properties. So now we're gonna talk about compressibility of fluid and vapor pressure. So basically, compressibility of the fluid is character to shrink in volume when increasing the external pressure. So the compressibility is referred to shrink in volume when we increase the external pressure. It is like bulk modulus. So as I've said before, bulk modulus is the measure of the decrease in volume with an increase in pressure. So the modulus of elasticity of a liquid varies depending on the specific gravity and the temperature of the liquid. So just now I've explained to you about the bulk modulus. Okay, so when we decrease the size, the pressure will increase. So how we want to calculate bulk modulus volume? So the formula I've put there. So bulk modulus equal to negative volume times the change in pressure and the change in volume in meter cube. So when we want to calculate bulk modulus, we must have the three value, which is volume, change in pressure, and change in volume. So why we have negative sign in front of the equation? It is because bulk modulus is decrease in volume. So the second volume will be smaller than the first volume. Okay, the last volume will be smaller to the initial. So when we minus the final volume and the initial volume, we will get a negative number. So that's why we put negative, because we want to get a positive value of bulk modulus. Okay, so that's why there is negative, because the change in volume will result a negative values. So that's why we put negative sign. So it is the same table that I've said before. So nowadays there is many reference books, and also we can find the value of bulk modulus, value of vapor pressure, value of surface tension. So all of the value we can just search in the internet, or we can find in a reference book. So nowadays it is easy for us to find this value, but although it is easy to find the value, we must know how to calculate it. So it is an advantage of our generation. Okay, it is easy to find all this value because we have internet. So that's all of the definition of compressibility of a fluid. So now let's move on to vapor pressure. So first thing first, I would like to define vapor pressure. So vapor pressure is a pressure exerted by a vapor when the vapor is in equilibrium with the liquid or solid form, or both of the same substance. So it is basically a pressure exerted by a vapor, but it is happen when the vapor is equilibrium with the liquid or solid of a same substance. Okay, so vapor pressure is a measure of the tendency of a material to change into the gases or vapor state, and it is increased with temperature. Okay, so next, the temperature at which the vapor pressure at the surface of a liquid becomes equal to the pressure exerted by the surrounding is called the boiling point of the liquid. Okay, so now I think we all know about when we boil a water, it will transform into a vapor state. Okay, so vapor pressure is a pressure exerted by the vapor surrounding the liquid, but when the vapor pressure on the surface of a liquid equal to the pressure exerted by the vapor surrounding, so that's what we call boiling point, the point when the temperature when the when the vapor pressure on the surface equal to the external surface. So that's why the water can evaporate, can boil. Okay, so they can boil and transform into vapor state because because they achieve boiling point. So we can see at the image. Okay, so on the left side, the evaporation. So bubbles cannot form since the vapor pressure is less than atmospheric pressure. So that's why when we don't boil the water, there is no bubble, okay, in the liquid, because the vapor pressure is less than the atmospheric pressure. But when we boil the water, the temperature increase, there is bubbles can form and rise since the vapor pressure can overcome the atmospheric pressure, which is the surrounding. Okay, I have said just now the external pressure on the liquid. So that's why when we increase the temperature, the vapor pressure increase and there is some bubble form in the liquid. So that is the vapor pressure. Okay, the pressure exerted by the surrounding. Okay, so I think that's all for the explanation of vapor pressure. So now I would like to talk about the factors that affect vapor pressure. So first, surface area. So the surface area of of the solid or liquid in contact with the gas has no effect on the vapor pressure. So when the surface area increase, the water will be easily evaporate. But the vapor pressure, the surrounding pressure is still the same. That's why the definition said that the surface area in contact with the gas has no effect on the vapor pressure because the vapor pressure is still the same, the surrounding pressure. So although there is change in surface area, there is no change in vapor pressure. So next, temperature. At a higher temperature, more molecules have enough energy to escape from the liquid or solid, and at a lower temperature, fewer molecules have sufficient energy to escape from the liquid or solid. So when the temperature is high, there is high energy. So the more molecules have enough energy to escape from the liquid or solid. But at a lower temperature, there will be lower energy. So that's why fewer molecules. Okay, so the molecules is lesser. So fewer molecules have sufficient energy to escape from the liquid or solid. So that is the second factor. So the lastly is the type of molecules. So the types of molecules that make up a solid or liquid determine its vapor pressure. So if the intermolecular forces between molecules relatively strong, the vapor pressure will be relatively low. But when the intermolecular force between molecules relatively weak, so the vapor pressure will be relatively high. Okay, so when the force between molecules is strong, the vapor pressure will be low. But when the force between molecules weak, the vapor pressure will be high. Okay, so how we want to calculate the vapor pressure of the solution? Okay, so there is a formula. So the vapor pressure of solution is equal to the mole fraction of the solvent in the solution times the vapor pressure of the solvent. So I think that's all the factors of that affect the vapor pressure. Okay, let's move on to the section B, which is the dimensional analysis and modeling. So the vapor pressure is the end of the section A. So first, I would like to talk about dimensions and dimensional homogeneity. So before that, I want to define dimensions. So dimensions are a measurable extent of some base quantity such as length, time, mass. Units are labels for different dimensions and combination of dimensions such as kilogram and Newton. So basically dimension is a measurable quantities and units are the label for different dimensions. So that is the difference between dimensions and the units. Okay. So next, dimensional homogeneity. So dimensional homogeneity is the concept where the dimensions of variables on both sides of equation are the same. If the units are the same, the dimensions of each term must be the same. So every valid equation must be dimensionally homogeneous, which is all additive terms on both sides of the equation must have the same dimensions. So that is what we call dimensional homogeneity when the units of both sides of an equation is the same. So there is an example which is length over times time. So when we do the calculation, so the final answer will be length over length. So that is what we call dimensional homogeneity, which is on both sides of equation, the dimension must be the same, dimensionally homogeneous. So I think that is the definition of dimensions and dimensional homogeneity. So now we want to talk about dimensional analysis and similarity. So dimensional analysis, also known as a factor label method or unit factor method, is a method to convert one different type of unit to another. So we can convert to a different unit, but their values are the same by using conversion factor. So this is the application of dimensional analysis. So for example, we can convert 1000 gram to a kilogram. So 1000 gram equals to 1 kilogram. So that is the application, the easy application of dimensional analysis. So next, conversion factor. Conversion factor is a numerical quantity that we can multiply or divide to the number or quantity that we want to convert. So just now I've give you a simple example, which is we want to convert gram to kilogram. So next, for example, you are cooking a soup recipe that requires 100 ounce of chicken broth. Unfortunately, the grocery store is only selling chicken broth by the pin. So how many pins of chicken broth are required to make the soup? So that there is when we have to apply dimensional analysis. So how many pins should you purchase? So the hint is use the conversion factor. 1 pin equal to 16 fluid ounce. So that is how we apply dimensional analysis in our daily life when we want to convert value to different unit, but the value stay the same. So that is dimensional analysis and conversion factor. Basically, dimensional analysis is very useful for planning, presentation, and interpretation of experimental data. It is also a method for reducing the number and complexity of experimental variables that affect a given physical phenomena. So using dimensional analysis, it is give us a simple way to interpret experimental variable. So there are three main applications of dimensional analysis. So first, to check the consistency of a dimensional equation. Second, to derive the relation between physical quantities in physical phenomena. Third, to change units from one system to another. So there are also limitations for dimensional analysis. So which is, first, it doesn't give information about the dimensional constants. Second, the formula containing trigonometric function, exponential functions, and logarithmic function cannot be derived. So it gives no information about whether a physical quantity is a scalar or a vector. So there is the main applications and also the limitations of dimensional analysis. So basically, dimensional analysis is very useful for us engineer to interpret experimental data and such, and when we work we have to interpret a bigger data. So dimensional analysis is very useful for us. So next topic, which is the method of repeating variables and the Buckingham-Pi theorem. So first thing first, I would like to define the Buckingham-Pi theorem before I move on to the method of repeating variables. So Buckingham-Pi theorem: if a physical process satisfies the PDH or the principal dimensional homogeneity and involve n, which is the dimensional variables, it can be reduced to a relation between only r, which is the dimensionless variables, or pi. So basically, when the physical process satisfy PDH and involve dimensional variable, it can be reduced to a relation between dimensionless variables. So next, the reduction m equal to n minus r equals to the maximum number of variables that do not form a pi among themselves and is always less than or equal to the number of dimensions describing the variables. So basically, this is how we want to calculate how much the dimensionless variable, which is the pi, how much pi there will be in the equation among themselves. So next, one way to determine the pi, which is the dimensionless variables, is method of repeating variables or exponent method. So after this, I will explain to you how to find pi using this method. Okay, so I will explain further and more detail in this method. So that's all for the definition of Buckingham pi theorem. Basically, it is about dimensionless variables. So now I will explain further how we want to use the exponent method or the repeating variable method. So our goal is we want to calculate how much is pi available in the equation or in the process. So under certain conditions, wind blowing past a rectangular speed limit sign, so it can cause the sign to oscillate with frequency, which is the symbol is W. Assume that frequency is a function of the sine width B, sine height H, wind velocity V, air density rho, and n elastic constant, which is K, for the supporting pole. So the constant K has the dimensions of FL. So develop a suitable set of pi terms for this application, which is just now we have learned about Buckingham pi theorem. So this is how we want to calculate, how we want to develop a suitable set of pi. So first step of exponent method is identify variables governing the problem. So we have to analyze the problem, you have to find the variables in the problem. So next, the second step is list the dimensions for each variable. So pick FLT since the dimension of K are FL. So you have to list all the dimensions for each variable, which is the frequency 1 over T, B is L, H is L, volume is L over T, and sorry, it's not volume, it's velocity. So next, rho, which is the density, is equal to M over length cube. So density is equal to Ft squared over L to the power of 4, and K is FL. So noted that F equal to MA, so M equal to F over A. So A is L over T squared. So therefore we can get M equal to Ft squared over L. So that's why you can get the density is Ft squared over L to the power of 4. So that is the second step. So move on to the third step, which is we can find the number of dimensionless product, which is the pi terms. So just now I've mentioned to you how we want to calculate the dimensionless product, which is the number of variables 6 minus the number of dimensions 3. So 6 minus 3, we can get 3. So the number of pi term is 3. So that is the third step. So move on to the fourth step. Select the dependent variable and the repeating variable. So the dependent variable is frequency, and the non-repeating variables is H and K. And the repeating variable is, we use the BL, VT, and rho is F. So that is the repeating variable. So the fifth step is use velocity to eliminate T, use B to eliminate L, and use rho to eliminate F. So then form a algebraic equations involving the exponent as follow. So we can see the pi1 is equal to frequency BV rho, and the pi2 is HBV rho, and pi3 is KBV rho. So we can we have to find the dependent and non-repeating variable and the repeating variable to form an algebraic equation. So we can see that for pi1 the frequency is the dependent variables, in pi2 H is the non-repeating variable, and pi3 is the K is the repeating non-repeating variables, and all the B, V, and rho is a repeating variables. So next I will talk about the next step. So next, the sixth steps is to form the pi terms by making each pi terms dimensionless. So exponents sums to 0 for each dimension and for each dimensionless product. So we have to find the sum of exponent, and we have to the sum of the exponent we have to equal to 0. So we can see for the first pi, so frequency times width times velocity and times rho. So we can see the full equation, which is 1 over T times L over T, and all that equation. So we have to express the exponent, which is -1 for the frequency, for the t in frequency, which is -1 and +0. So -1 +0 -b +2c is all for the t variable. So next for f and for l, so we have to list all the exponent for each variable, which is for t, f and l. So when we solve the exponents of a, b and c, we can find the value of a, which is 1, b is -1 and c is 0. So that's why we can conclude that pi1 is equal to frequency times width over v, because b is -1, that's why we over v, because v is -1, the exponent is a -1. So next, the seventh step is to find the value of p2. Okay, the equation for pi2, equation for pi2. So pi2 is h times b times v times rho. So the equation is stated there, which is l in l over t and all that. So we have to express the exponent for each variables, which is for t, f and l. So after we solve all the exponents a, b and c, we found out that a is equal to -1, b equal to c equal to 0. That's why we can conclude that is pi2 is equal to h over b. So the last step is the same as the sixth and seventh step. We have to express the exponent but using the third algebraic equation that we developed before this. So the pi3 is equal to k over rho b to the power of 3 and v to the power of 2. So at the eighth step, we can conclude that we have the equation for pi1, pi2 and pi3. So for summary, pi1 is equal to frequency times b over v, pi2 is h over b, pi3 is equal to k over rho b to the power of 3 and v to the power of 2. So that's all the 3 pi that we have to find. So now we have finalized our answer. So let's move on to the dimension. Okay, so we want to form a dimensionless equation, so that's why we have to check the dimension, which is the pi1 is 1 over t times l times t over l. So after we do the calculation, it will be dimensionless. So it is the same for pi2 and pi3. All these three equation will be dimensionless equation, which is pi. So that's all the steps in method of repeating variable. So this is how we use exponent method. So this is how we calculate Buckingham pi theorem. So I hope you all understand each steps to find the equation for pi. So that's all for the Buckingham pi theorem and method of repeating variables. Okay, so now we have reached to the last topic of dimensional analysis and modeling. So now we have to define dimensionless terms. So dimensionless quantity is a quantity to which no physical dimension is assigned, also known as a bare, pure or scalar quantity, or a quantity of dimensions or a quantity of dimension 1 with a corresponding unit of measurement in the SI of the unit 1, which is not explicitly shown. So basically, dimensionless term is dimensionless. So before this, we have learned how to find the Buckingham pi theorem, which is the dimensionless terms, which is the pi. So for example, 1, I, pi and e. So this is all dimensionless terms, which is they have no dimension. So I think that's all for the definition of dimensionless terms. So I think we have reached to the end of the presentation. So I hope that my presentation is good and all of you that watch this video can understand what I want to deliver to all of you, which is in section A we have discussed on the fluid properties, and section B we have discussed on the dimensional analysis and also the modeling. Okay, so I hope both section, so the information is in both section, you can understand, and I hope you can apply in your study and daily life. So that's all from me. Thank you.